So in today's lecture, we are going to see what is continuous and discrete time signal in more detail. We will be seeing what is a continuous time and a discrete time sinusoidal signal. And we will be seeing what is the significance of frequency and signals. Then followed by we are going to see what is sampling and aliasing effects. So in sampling and aliasing effects, I'm going to be talking about some interesting theories that go with what is required to do the DSP properly. So that is what is called as Nyquist rate or your sampling theorem, and we are going to see a lot about it in today's class. So before we get started on this continuous time and discrete time signal, I would like to talk to you what is a signal. So a signal definition is any physical quantity that contains information, and that information can be about a system, about a system's behavior, about how to communicate with that system. So that is what we call as a signal. So a signal contains information in some pattern which can be extracted and processed using our signal processing. Now, in signal and signal processing, we have what is called as a time independence. So we are having the x-axis, which is always time, and that is an independent variable, meaning your system performance is not going to change with time. So that is what is time independent means. So the opposite to it is time dependence, where the system performance varies with different time. So an example is a solar panel. So according to the sunlight, the performance will keep changing. So that is not exactly a time independent system. But now when I talk about DSP, we are mostly, I wouldn't say every time, but most of the time there is always exceptions like the solar panel, which is also can be modeled as a DSP system. So there are most of the things happen on time independent concept or notion. So an example of a time independent system is x of t plus 2 of t, whereas a time dependent signal example is t into x of t. So that t into x of t makes it a time dependent because according to the change in time, your system is gonna behave different. Now we're gonna see these signals which are in time domain, where the time is your independent variable, can be either a continuous time signal or they can be a discrete time signals. So both these signals are derivative from this time domain notion, and this means that the derivative means the continuous signal and the discrete signal are derived from that time domain signals, and in the order of time domain, continuous time and discrete time signals. So your discrete time signal is derived from your continuous time signal, and it is only defined on discrete intervals as shown here. 0, 1, 2, 3, 4. A continuous time signal exists in time or exists in any instant of time. It exists at 0.1, 0.001, 0.0001. Any instant of time, your continuous signal exists. Good. Now, what is a sinusoidal signal and why it is very important compared to the other standard signals such as ramp, step, and exponential signals? So sinusoidal signals are like the building blocks of your DSP. So you use every DSP algorithms or most of the DSP systems, they operate on sinusoidal signal, and the reason for the significance of the sinusoidal signal is one, the fidelity, and the second one is the less distortion. So what do you mean by fidelity? So the fidelity states that whenever I differentiate or integrate sine or a sinusoid, I am going to get a sinusoid output. Or to be a generalized statement would be like a sinusoid produces sinusoid output. Whenever you send a sinusoid input to your DSP system, most likely you will be getting a sinusoid output. And this property is called as the fidelity property of the sinusoids. And the next is the less distortion. So sinusoids have smooth slanted edges, or the smooth transitions from the highs to lows. So whereas on a square wave you have a sharp turn. So whenever, even while you're driving a motor vehicle, whenever there is a sharp turn, you have to take extra effort to make that curve. But on the other hand, if you have a smooth curve, you make it in a very quick manner. So the same concept which is applicable to the sinusoids, and that's what makes sinusoid very, very useful. Good. And now we will see what is a continuous time sinusoid and what is a discrete time sinusoids. And in this, I'm going to ask you a question. Among this trigonometric signals, which are like sine, cos, secant, arctangent, cosec, why sine and cos is more popular? So they are complementary because, okay, so since this is a YouTube lecture, I'm going to tell the answer is because they are orthogonal. So the orthogonality of sine and cos is another property, and I leave that for your self reading, or maybe I'll explain it in the next coming lectures. So we'll see what is a continuous sinusoid looks like. A continuous sinusoid is represented in the form x of t is equal to cos omega t or sine omega t, where omega is equal to 2 pi f, because the sine and cos full cycles are in 2 pi. Okay, so these 2 pi cycles of sine and cos also define the frequency of the signal. For an example here, we have sine of 4 pi t, so which means you are having 2 pi. So 2 into 2 pi is 4 pi, so you are having 2 full 2 pi cycles, and that is what I have shown you. So you are having 2 full cycles, 1 and 2, and that is for sine 4 pi t. Now for example, I'll take another example. A very similar analogy goes to sine 6 pi t, which can be represented in 3 full cycles of 2 pi. And that means your frequency is, this is gonna, we can just say right now that is also the frequency of the signal. So for your first case, sine 4 pi t, your frequency is 2, and for sine 6 pi t, your frequency is 3. Now, next we are going to see what is a discrete time sinusoids. A discrete time sinusoids are of the form sine omega n. So where your t in the continuous time is getting replaced with n. So where n represents your samples, or the discrete time samples extracted from continuous time. That's a lot to take. So we can, for now, we'll just call them as samples. So we have seen what does discrete time sample mean in the lecture 1. So I'll just say that as discrete time sinusoids can be represented as cos omega n and sine omega n. So here your omega is equal to 2 pi fn. So meaning it is the same. It is going to have 2 pi cycles. The same, we can just, for the explanatory purpose at the intro explanation for this can be said in the same way I explained your continuous time sinusoids. Good. So if the frequency is high, so now we are going to see the omega can be having pi by 8, pi by 4, pi by 2 and pi, and the frequency accordingly will vary as 1 by 16, 1 by 8, 1 by 4 and 1 by 2. So whereas contrary to this continuous time sinusoids, your frequency is in integer, whereas in discrete time it is in fraction, or it is in rational number. And now I would like to tell you something, that whenever the frequency is high, you have more number of cycles, as you can see here, and when the frequency is less, you have less number of cycles. So that brings us to the definition of frequency. So we are going to see what little bit about the frequency that was covered in continuous time sinusoids and discrete time sinusoids. So what a frequency of a signal means is, it is the number of repeating cycles per second. So the importance of frequency is too much, because every the information, you can talk about the information, you can talk about what do you call, you can talk about the effects, you can talk about the what effect a signal can cause, all that depends on the frequency it contains. So let us take, for example, signal shown on the left side, and I am going to convert that using frequency transform. I'm going to obtain the frequency representation of the signal, and I'm having a lot of frequency bands. So if you see, I'm having low frequencies, mid frequencies, and high frequencies. So this means that my input signal consist of all three frequencies. Now I can separate these frequencies using DSP. In DSP, I have a low pass filter which passes my low frequency. I can have a band pass filter for the mid frequency, and I can have a high pass filter for my high frequency. Now, if I separate these frequencies and use them separately, I can use them for various purposes. A low pass filter can be used for just the information. A high pass filter can be often considered as a noise, as a background noise, like the sound of the fan, sound of the moving vehicle. So if I get rid of the high frequencies, or if I use a high pass filter, it is also get rid of these background noises. So that is one application of this frequency. So this just tells you what is the importance of frequency in your signal processing. So we're going to see a lot of frequency transformation techniques, a lot of the things that work with frequency, a lot of application areas where this is useful in the coming in the units 2 and 3. Now I have another illustration for your frequency. I have a sinusoid here, and now I am segregating it into full cycles. So let us see how many full cycles. So how many V shapes are we having in this graph? So we are having 6 V shapes. So now the frequency is defined as the number of cycles per second. So we are going to stress on that divided by second. So even though the number of cycles is 6, the time duration of that signal should be 1 second. If the time duration is a 2 second, then your frequency is obviously not 6, it's 6 by 2, it's equal to 3. So this notion should help you understand what a frequency is and how frequencies are useful in signal processing, and how you can find a frequency of any given signal. You can just, in this case it's straightforward, you can count the number of cycles. In most of the cases you cannot count. In that case you need to take transformation. You need to apply something called as a DFT, which is a discrete Fourier transform. A discrete Fourier transform has a peak at the frequency which tells us what frequencies are contained in your signal. So that is the frequency highlighting property of your DFT. Next we have sampling of signals. So we are going to see the block diagram illustration for the sampling of signals. So when I say we are sampling a signal, what do I mean is you are taking a continuous time signal and you are discretizing it using a sampling time period. So the time period that is given here, t, that is your sampling time period. So this n of t is your sampling interval, and c to d is your continuous to discrete transformation. Good. So this process, this whole illustration allows us to take a CT signal, convert it into a DT signal, and this DT signal can be used for DSP or digital signal processing. Now for the sampling to be effective, we are going to see something called as a sampling theorem. So the sampling theorem, what it states is we need to know two things. For sampling theorem, you need, one is your signal frequency, the next one is your sampling frequency. So your signal frequency is the frequency of xc of t, and your sampling frequency is the time period. So we're going to see where this and how the sampling theorem can be derived using these two frequencies. So now the definition of sampling frequency states that it is equal to the number of samples per second, just like your frequency is equal to the number of cycles per second. So now we are going to see both these signal frequency and sample frequency on this graph. Now if I take a 1 second duration sinusoid, and then I'm going to take 13 samples on that signal. My sampling frequency is equal to 13 divided by 1 second. Now for the signal frequency from previous slide, you know the signal frequency is 6 cycles per 1 second, which is equal to 6. Now we are going to take these two numbers 6 and 13, we are going to take it to the next slide, and then we are going to see So now we want to see how these two numbers come into sampling theorem. So your sampling theorem is also known as Nyquist theorem and just simply states that if the sampling frequency is greater than twice your signal frequency, then it's good, then it's all good, you don't have any problem, right? What problem? We are talking about aliasing. So we are going to see what is aliasing also, but before that let us see these two numbers 13 and 6, so whether this criteria of sampling theorem or the Nyquist theorem is met. Yes, so if 13 is greater than obviously 2 into 6 12, so our sampling theorem works, which means we are all good, we don't have the problem of aliasing. So if sampling theorem or your Nyquist theorem is not satisfied, then you have to deal with aliasing. And what is aliasing? Aliasing is nothing but your spectral overlapping. So your frequency spectrums overlap with each other, and that is your aliasing. So we are how is that going to happen when this sampling theorem is not met or not satisfied? So that means the sampling theorem Fs is less than 2n, right? You're going to see that also. So now when I say Nyquist rate and sampling rate, so this is a question commonly asked to test your knowledge. People say, what is the difference between a sampling rate and a Nyquist rate? As you can see, when I say Nyquist rate, I'm only talking about Fs greater than 2Fn. The Fs less than 2Fn doesn't come in Nyquist rate. So on sampling rate, we include all the frequencies. Good. Now we have aliasing. So the aliasing process, what is aliasing? So when you have enough number of sample points, so when Fs is greater than 2Fn, or when you have more sample points, your input signal is approximated properly, right? So what is this approximation? What is all this? So it is the best understandable in the next slide, just if you can wait. So just I'm taking this Fs greater than 2Fn means more sample points, and more sample points gives more or the best approximation signal. Now this condition, when Fs is less than 2Fn, this is your not your Nyquist rate. Your Nyquist rate or the sampling theorem is not satisfied. So we will see what is going to happen. So this will tell us clearly the problems with not maintaining your Nyquist rate. So let us say I am having 6 cycles, so I need to select less than 12 samples. So I'm going to select only 6 to 10 samples. So I have selected just 6 samples in this case, so less number of samples. And now in my reconstruction, if I draw the signal, what do I see? I don't see that signal to be anywhere close to my original signal. So that signal is like totally different. It's like the shape of the signal has changed. And now you see another important thing is the number of cycles. So how many V's you have? You don't have 6 V's, you have only 1 V, right? So the number of cycles per second is just 1. Before it was 6. So your shape of the signal has changed, your frequency of the signal has changed just because you didn't maintain the Nyquist rate. That is your Fs greater than 2Fn. Clear? So these are the disadvantage, or we call these as the aliasing problems in time domain. So we are still in the time axis, the independent variable time. So we still haven't seen why, but we are talking about Fs and Fn, and these are your sampling frequencies and your signal frequency. So, but why we are talking in the time domain? So let's go to the frequency and see what's happening in your frequency. In frequency is where your aliasing is causing big problems in spectral overlapping. So the spectral overlapping is one of the biggest problem with aliasing, and we will see what it is in this slide. So I'm having x of t, and then I am multiplying. So what sampling does is it takes your x of t, or it takes your continuous signal, and it multiplies it with your delta signal, right? Your delta signal is nothing but your sampling signal. Good. And when you multiply these two signals, what is going to happen? So it is just your number multiplication. So multiplying two signals is nothing but you're multiplying them as two numbers. So after multiplication, you're going to see something like this. Good. Now this is my multiplied signal, or this is my sample DT signal. And where is aliasing in the sampled signal? So let's go now. So now I'm going to take the FT, the Fourier transform, or the frequency transform of these signals separately. So for my x of t, my frequency transform is going to look something like this. Fn represents the signal frequency, minus Fn and plus Fn shows us that the signal is symmetric and the signal is band limited. And then for the pulse train, which is all ones, if I take the Fourier transform, I'm going to get a Fs to Fs, where Fs is the signal frequency. The Fourier transform, or the frequency transform of your delta or pulse train or an impulse, is just a delta or impulse, right? So there is no change in the Fourier transform. And now what is going to change is, before, what was your multiplication in the time domain is now convolution in frequency domain. This is a very important property that is discussed only in the Fourier analysis of signals. So what that property is the multiplication and convolution are the equivalent. So if you do multiplication in the time domain, then it is convolution in the frequency domain, and if you do convolution in the time domain, it is multiplication in the frequency domain. So now let's go to this notion of, so what will happen is, in the time domain we were multiplying the signal. So now when I take the frequency transform, I am going to convolute the signal. So when I say convolution, what I am going to do is I am going to scan this one signal with the other. So when I convolve these two signals, so I am going to get something in this manner. So the convolution of those two signals gives us this output. Now I am taking this convolution output, I am going to study it one by one. So let us just take one hat function, see what is happening. So this is how your convolved signal looks like, minus Fn, Fs and Fn. So here the width is 2Fn. Good, got it. Now let us take 2 hat and see what's happening. Now you have 2 hat function, and this 2 hat Fs and Fs, and then this becomes Fn, Fn, and this is your Fn. So now if you see the space, this is Fs, and your this space is Fn, and that one is Fn. So here when you take 2 hat functions, you get Fs is equal to 2Fn, and that is your ideal critical sampling. So when Fs is equal to 2Fn, you can see that your spectrums just are at the boundary. So there is no overlap, but that also is the case where you have no overlap. If you go Fs less than 2Fn, then your spectrums come closer to one another, and then you are having the overlap. Okay. This is how your overlap signal looks like when Fs is less than 2Fn. So whenever that overlap happens, this width is going to be less than 2Fn, and that is when your sampling theorem fails. So your sampling theorem is not satisfied, means your Fs is less than 2Fn, and that is what it means. Now, when Fs is greater than 2Fn, as you can see here, clearly the spectrums don't overlap. In fact, there is ample gap between the two spectral hat functions. And this is your aliasing or your spectral overlapping. But when Fs is less than 2Fn, you get spectral overlap, and that is not good because that will distort your signal. And this is also what is called as aliasing. Good. So that is for lecture 2. I'll see you back with lecture 3.